Okay, so I guess we should get started. I guess I should say welcome to Conquering C++ 20 Ranges. So my name's Tristan. Welcome really to a guide to Conquering C++ 20 Ranges. It's probably a better title, probably a slightly more modest title. The C++ 20 Ranges is a mountain. I want to help you conquer that mountain. Can help show you the path. I can warn you about some pitfalls along the path, but the road is not easy. So it's a guide to conquering C++ 20 ranges. We've only got an hour together. This is not sort of a multiple day workshop. So we'll do what we can over the next hour or so. Some of you will know, I'm sure, this is not my first time talking about ranges at CppCon. In fact, this is part 3 of a trilogy of talks. It wasn't really planned as a trilogy, just ended up that way. So there I am in 2019. This is back. Remember when we could do these things in person? I'm very envious of those of you who are there today in person. I wish I could be there. Sadly, travel restrictions mean I can't. But there I was 2 years ago. I gave a talk called An Overview of Standard Ranges. There's a YouTube link just for when these slides go out later. And this was, as the title suggests, really kind of a broad brush overview of the new facilities which at the time were proposed and now part of C++ 20. And I followed that up last year with a talk entitled C++ 20 Ranges in Practice. So this was a slightly different tack from the first talk. In this talk, I sort of used this idea of investigating a few little leak code style problems and using ranges to solve them, and using those to investigate sort of different areas of ranges that people might not have been familiar with. So that was last year's talk. This year, we're back for part 3, Return of the Jedi, Return of the King, whatever, the part 3 of the trilogy. The big finale, the grand finale, we've upped the game. This is Conquering C++ 20 Ranges, or at least a guide, a helping hand along the way to doing so. Okay, so this was the second talk, C++ 20 Ranges in Practice. If you haven't seen either of these two talks, don't worry. So this talk, I do assume some ranges familiarity. And these days, because it's been shipping for a couple of releases in GCC and also in MSVC, I think more people are familiar with ranges than were in 2019. And Range v3, of course, has been around for a long time now. So if you haven't seen these two talks, don't worry. I hope if you've got some familiarity with ranges, then I hope you get something out of today's talk. If you're completely new to ranges, then these two talks are, or at least are intended to be, a good place to start, particularly the first one as a broad brush overview, and the second one slightly more in depth. So today's agenda. So as I said, in the second talk, last year's talk, I had this the approach of, we had these 3 little programming problems, leak code style problems, and I used ranges to solve them, and we used that to investigate different areas of ranges. And people seem to quite like that. I got some nice feedback. So if it ain't broke, don't fix it. So that's what we're going to do again today. Just one thing I just want to warn you at this point. This is quite an intense session. The slides are pretty code heavy. There's going to be a lot going on. I do have a lot of material. It's one of those things where you start off, you submit your presentation, it gets accepted, you come to write your slides, and you realize your talk is 3 hours long. So I have condensed it down as much as I can, but there's still a lot to get through. So we're going to be going quite fast, but I hope that's okay with everybody. So today's agenda, we're going to look at 3 little programming problems, just as we did last time. The first one is called Fibonacci Fun. No prizes really for guessing what that one is about. Then we're going to have string trimming revisited. So if you have seen last year's talk, you'll know I did a bit about string trimming. We're going to look again at this problem and look at solving it in a slightly different way, or look at solving part of it in a slightly different way. And then finally, I've got this sort of enigmatically named problem called dual shifting. This has nothing to do with the gearbox in your car, but we'll get to what I mean by dual shifting in due course. So onwards, Fibonacci fun. This is a pun, by the way. Fun as in enjoyment, fun as in function. What can I say? I'm sorry. It's been a long week. Right. Here's the problem statement. Here's the problem we want to solve. So, given positive integers n and k, print the first n elements of the Fibonacci sequence, which are also exactly divisible by k. So, for example, if n was equal to 5 and k was equal to 3, our output should be 0, 3, 21, 144, 987. So these are the first 5 elements of the usual Fibonacci sequence, which are divisible by 3. Okay, so I'm sure most people are familiar with the Fibonacci sequence. If you're not, it's this sequence that begins. Doesn't always include the 0, but in this case I am. So 0, 1, 1, 2, 3, 5, 8, 13, 21, etc. Where each term after the first 2 is calculated as the sum of the 2 previous terms. So you probably are familiar with this because this comes up all the time in programming exercises, particularly the beginner exercises is quite often used to introduce the idea of recursion, because you can write this with a recursive function. So we're going to have a look at Fibonacci, and we're going to solve our problem initially like this. So this is my fibfun. There are many ways that we could approach this problem. This was just the first way that occurred to me, the easiest way I could think of going through and printing the first n elements of the Fibonacci sequence, which are divisible by k. So we can see very quickly we've got our 2 Fibonacci variables, the current variable and the next. And then we're going to loop through until we've found n solutions. And we're going to check whether our current value is divisible by k. If it is, we're going to increment our found counter and we're going to print out the value. And then after that, we're going to actually do our Fibonacci update, our Fibonacci iteration. So this, if you haven't seen standard exchange before, it's a really useful little utility. So it's, I think it came in C++ 17. So what this is doing is it's assigning the value of cur plus next into the variable next, and then it's returning the old value of next. So standard exchange, it's one of those things that you never knew you needed it, but once you start using it a bit, you start to see uses for it all the time. And this is one of those uses. So it does the whole Fibonacci thing in one line, which is rather nice. So we can run this code. We can call fibfun of 5 and 3, and it prints out the numbers just as we wanted. So this is fine. This solves the problem. This is all right. And of course, this is all right for a one-off piece of code for a leak code problem or something. But more generally, I have to be honest and say, I don't really like this code, even though I wrote it, right? And the reason I don't like this code is because this is, about 10 lines or so. Simple function, but really this function is doing 4 separate things. So first of all, we're calculating the Fibonacci numbers, calculate the Fibonacci sequence, right? Then we're checking which of those numbers are exactly divisible by k. Then we're counting how many of those numbers we found. And finally, we're performing some operation, in this case, printing. So this little function is doing 4 separate things. And you have to, okay, this is a small example, but more generally, you have to kind of search around. If you wanted to change one of those things, you have to kind of search around, hunt around in the function to change the one bit that needs altering. So I think, even though this is a simple function, yes, to be honest, this would be absolutely fine. We're going to take, as a general principle, we're going to see how we can try and improve this little fibfun. So the first thing we're going to do is we're going to abstract out our generation of our Fibonacci sequence. So we're going to write a little Fibonacci generator class, a little function object. So we've got our Fibonacci generator. It's just got two member variables, cur and next. These were the local variables in our function. And then we've got a function call operator. And you can see what it does. We save the current variable. We do the Fibonacci update using standard exchange as we did before. And then we return our saved variable. And OK, we can update fibfun to use the generator. And there we go. You can imagine, like, perhaps you can look at this and start thinking, OK, well, maybe we pass a generator into this function. Maybe it's a generic function. We have different generators that have the same interface, that kind of thing. But you can see that in the while loop, we're having to save the result of gen into a local variable. And the reason for that is because we want to use this value twice. Once to test it, and once, if the test is successful, to print it. So we need to use val twice, but every time we call the function call operator on gen, it's going to give us a new value, and the old value is just going to disappear into the ether. So we need to save it into a named variable. So perhaps there's an improvement we can make to our little Fibonacci generator. Perhaps instead of having a single function which both updates and returns a new value, like we have here, perhaps we can have two separate functions to do this functionality. Perhaps we can have a function called get, which just returns the current value, and a function called next, which returns the next value. So sure enough, and you can see actually we've kind of tidied up our implementation of our fib generator a bit doing this as well. We no longer have to do that horrible thing with the temp variable. If anything, this is a nicer implementation than we had before. So sure, we can update our fibfun to use our new version of the fib generator. And sure enough, we can call get a couple of times rather than using this local variable. And we can call gen.next at the end of the loop. Sorry. We can look at this fib generator and we can say, OK, we've got an operation that gets the current value. OK, we've got an operation that gets the next value. These are kind of quite familiar ideas. And if I make a couple of changes to this little generator, perhaps they become even more familiar. Perhaps if I renamed get to operator star, and perhaps if I renamed next to operator plus plus, perhaps this would start to look like something we're very familiar with indeed. Because we very, very nearly have an iterator here. Right, we're very close to the iterator interface. So, OK, we've got this far. Why not? Let's take this up a notch. Let's actually implement a Fibonacci iterator. Turn our fib generator into a fib iterator. So to do that, the first thing we need to do is add a little bit of boilerplate. We need to add a couple of type defs. There are only two of them that are mandatory in C++20. And those are the value type, which in this case is size t, and the difference type. We don't really have a meaningful difference type, but we're just going to default to standard pointer diff t. And the other change we need to make is to update our operator plus plus. It now returns the fib iterator. So, OK, so far so good. I reckon this is pretty close to being an input iterator, at least. So let's try. OK, let's see, because I'm pretty sure I got that right. Yeah. Let's statically assert. Let's static assert that our fib iterator is indeed meets the syntactic requirements of a C++20 input iterator. Did I get everything right? Oh, no. OK, so I forgot something. And we can see at the bottom that we can see the required expression I++ is invalid. So I forgot to add a post-increment operator. My bad. But actually, the reason I wanted to show you this is because this is basically the exact error output that GCC 11 gives you. Right, I've trimmed the length of the include lines a little bit just so it fits a bit better horizontally. It still doesn't quite fit. I don't know why GCC likes printing the whole full path of your standard library headers because it's not very useful. But anyway, this is the whole error message that GCC 11 prints. And I think this is actually not too bad. People have had complaints about the the level of error messages that you get with concepts. But I have to say, at least in GCC, if you are trying to write a type like our fib iterator that matches some particular concept, then static assert really is your friend. If you try and work out the missing things by, let's say, passing a fib iterator into a function that expects an iterator, the error messages aren't going to work quite so well. But the reason I want to show you this is to show you that, hey, actually, this is pretty useful to statically assert these as you're working through, because it will very often, if you're lucky, in this case, it will tell you exactly what you were missing, or it will at least give you a hint as to what you're missing. So, okay, our fib iterator, we're going to give it a post-increment operator. C++20, this doesn't have to return anything in particular. We can just get away with returning void, and all we're going to do is call our pre-increment operator. So this is now a valid C++20 input iterator, believe it or not. So 18 lines, that's not too bad. There's a little bit of boilerplate, but it's not, I don't think it's too bad at all. But we can actually go one better, because morally our Fibonacci iterator is not restricted to being an input iterator. If we took a copy of our fib iterator, then those two iterators would have independent iteration states. We could iterate them, and changing one, advancing one would not change the other. Right? So we can upgrade our input iterator to a forward iterator. This requires a little bit more boilerplate, but it's not too bad. So we can see this is what we've had to add or change. So we now need a third type def iterator category. We set to forward iterator tag. This is the same as we've always had to do in C++ 98 and onwards, because input and forward iterators are syntactically the same. So we have to opt into being forward or better. And we've now had to give a proper implementation of operator + int. So this is a pretty standard way of implementing this. We just take a copy of this, we increment this, and then we return our temporary copy. So this is a pretty standard way of implementing this. And then the last thing we need to do is we need to be able to compare two iterators and say, do these two iterators refer to the same place in the same position in the same sequence? And luckily for us, the default, in C++20, we can default the comparison operator, and this is just going to do exactly the right thing. And it's even going to give us an operator not equals as well, all for free. So this is really nice in C++20. And with all these things in place, now our fib iterator is a readable forward iterator. And it's pretty nice, right? So we can update our fibfun to use this fib iterator and, okay, right. Well, maybe this isn't so nice because actually really nothing's changed. We've changed our function names. It's no longer .get, it's now *iter. It's no longer .next, it's ++iter, but actually this really hasn't helped very much at all. And this is where we found ourselves in C++ 98, right? We had iterators and we could do stuff with iterators, but there wasn't always a great deal of value in doing so. In C++20, of course, we have all these shiny new range adapters that I've talked about in the last couple of talks. But range adapters don't operate on iterators, range adapters operate on ranges. So what we want is not a Fibonacci iterator. What we want is a Fibonacci range, a Fibonacci view. So let's write a Fibonacci view. Okay? Actually, let's not. Let's not write a Fibonacci view, because in this case, we don't actually have to. The standard library comes with, in C++20, comes with facilities that save us from having to write this Fibonacci view. So what we can do instead is this. So by the way, on all of these slides, whenever you see RNG, that's just shorthand for namespace std : ranges. It's a lot to fit on a slide otherwise. It's a lot to type generally. So namespace RNG, shorthand for standard ranges. So what we can do is we can create a subrange to hold our Fibonacci iterator. So subrange is a type that's in C++20. It's basically a wrapper around an iterator and a sentinel. And in this case, our iterator type is our nice fib iterator. And our sentinel is this special magic thing called unreachable sentinel. I talked about this in the 2019 talk, showed how you can use this in some cases. If you're very careful, you can use it as an optimization. In this case, we're using it to say that this Fibonacci range now is an endless range. Right, we're just going to keep on spitting out Fibonacci numbers forever. Well, until size t overflows, in which case we'll start printing out the wrong Fibonacci numbers, but we've probably stopped caring about Fibonacci by then. Right, so now our views Fibonacci, our Fibonacci view, it is a range, it is a view, and it's started off by our fib iterator. It's saying it just goes on forever. So now that we have a view, we can start using all those really nice adapter types that are in C++20. So we can rewrite our fibfun into something really quite different. So we've got, what we're doing here is we've got our Fibonacci view, and then we're piping that into a filter adapter. So we've got our view that's going to have just an infinite sequence of Fibonacci numbers. We're filtering that, accepting only the elements that are exactly divisible by k. We're taking n of those, and then we are performing our output operation. This last line, if you haven't seen this before, this is just a fancy way of printing a range, copying to an output stream. I could have just used a for loop. I could have used a format. If I wanted the format lib if I wanted to, but hey. So now that we have a Fibonacci view, we can start using all of these really nice facilities. We can rewrite our fibfun into something that I think, personally for me, is easier to read, more maintainable, just a nicer form of code to work with. And I realize that's a matter of opinion and perhaps familiarity. So this was our original, and as I said, this function is doing 4 separate things, and we really have to hunt around to kind of work out what those 4 things are. With this version, it's immediately clear. The 4 things this function is doing are on 4 separate lines, and they're the only 4 lines in the function. So, you know, I got to say, I really like this. I think this is really, really nice. And okay, and as an aside, we've now got a reusable view that's going to generate Fibonacci numbers, an infinite sequence of Fibonacci numbers whenever we like, which is surely a very useful thing. Well, maybe not, but you can perhaps imagine how we could adapt this for perhaps other kinds of sequences, how we can adapt those into views. So this is just one technique I wanted to show you. I want to show you how we can use these ideas to transform a function into something that is subjectively, and I appreciate other people don't share my views, but subjectively for me, easier to read, easier to maintain. You know, just read straightforwardly from beginning to end, at least, in my opinion. So that was that was our first little problem. That was, I wanted to show you really one technique in which we can use a custom range adapter by not writing a custom range adapter at all, by reusing some of the facilities in the standard library. In this case, standard subrange, ranges subrange. So at this point, I was going to take questions. I forgot to say to you, please do put questions in the Q&A tab. I can see there's some chat. I can't really. I'm not going to read it all. I can see there's some chat, but if you do have any questions, please do put them in the Q&A tab, and I'll do my best to answer them. But since there don't seem to be any, we'll go on to problem number 2 to look at string trimming revisited. For those who saw the last talk, the third problem we investigated there was a question of string trimming. So this was a problem statement we had then. So given an input string, construct a new string with the leading and trailing white space removed. So for example, given a string hello world with some junk at the front, some junk at the end, we want to remove all that, and we want to just be able to say, just have the string hello world without all this noise at the front and back. Okay, so if you're on YouTube or so, you can go and have a look at this, how we originally solved this. But the final solution we came up with was something like this. So we had a customized trim front adapter, which was a specialization of this standard drop while view. Then we had our custom trim back adapter, which was a combination of first reversing, then trimming from the front, and then reversing again. And finally, we had our trim adapter, which was just trim front followed by trim back. So this second one, trim back, the way it works is that, well, we've got our built-in standard library provided drop while view that can drop elements from the front of a range. So we can make use of this by first reversing the range, then dropping from the back of the range, and then reversing again to get the equivalent functionality. And I said this was pretty nice. This is like a way we can combine adapters to come up with a new composite adapter. But I also said that in the ideal world, we wouldn't necessarily have to do that. We would be able to have a drop last while view that would just do this for us. And we wouldn't have to do this reverse trim reverse business ourselves. And the other thing I said last time was that if I had longer, I would have shown you an implementation of drop last while view. So the good news is I do have a bit longer today. So this is what we're going to look at next. We're going to look at drop last while view. So no messing about this time. We are actually going to write a class. As you can see, I've given us plenty of room to do this. So this is a class template. It takes two template parameters. The first one is the type of the underlying range that we want to adapt. So we're a range adapter. We're adapting some underlying range. It can be anything, subject to some constraints we'll see shortly. So that's a template parameter, and also our predicate is our second template parameter. So the first thing we want to do when we're writing a view class is we want to inherit from this view interface ranges, standard ranges view interface base class. So this is a CRTP base class. It's kind of weird if you've never seen it before. You're inheriting from something that's templated on the derived class that you're still defining. It's technique that's been around in C++ for quite a while, but it is quite strange when you first see it. But basically, it's C++'s or a way of doing mix-ins in C++. So if we inherit from this standard ranges view interface, we're going to get a few useful member functions basically for free. And the other thing we're going to do is to opt in to being a view. So I went through this in the last video, but we have to tell the compiler that we intend for a particular class to be considered a view. Okay, and there are a couple of ways we can opt into that, and one of the ways is by publicly inheriting from this view interface base class. So that's what we're going to do here. Okay, we're going to begin to flesh things out a little bit. So we're going to add a member v, that's our template parameter, and a member pred. That's the predicate. You might want to mark these with no unique address. This is just slide code. And we're going to add a couple of constructors, a defaulted default constructor, and a second constructor that just takes a v and takes a pred, and just moves them into our member variables. These, again, if you were trying to do this perfectly, you might take R value references here, but there we are. So far, so C++ 17, right? We need to start thinking about constraints. So one of the things I talked about last year is exactly what a view is and how we define a view. And I won't go over it all again, but views come with some semantic requirements. So concepts are a combination of syntactic requirements. These are the things that the compiler can check. And semantic requirements are things that we just kind of have to obey, right? And the semantic requirements of a view are that it is, its move operations and its destruction operations are constant time. That is, they're not dependent on the number of elements in the view. And also views don't have to be copyable, but if they are copyable, then the copy operation is also a constant time operation. So since we want our view to obey these semantic constraints, we're opting into being a view, so we're claiming we obey them. We really want to make sure we do. So we're holding a member of type V. If V was something like a standard vector, well, then our destructor, our copy constructor, would have to go and copy each member or destroy or copy each member of the underlying vector. So the way in which we can ensure that we meet the semantic requirements of a view is by making sure that our underlying type is a view. And we do that by adding this constraint, standard range view, to our template parameter V. That's why I named it V in the first place, right? Because I knew this was coming. The other constraint we want to add is that we want V to be a bidirectional range. So I conjecture that it is possible to do this for forward ranges. This is left as an exercise to the viewer. I conjecture that this is possible to do. But I haven't actually tried it myself. The other thing we're going to do is add a predicate to our, add a constraint to our predicates. So this is not on the exam, so don't worry. This is a concept that comes from the standard library. This tests that firstly that pred is a predicate, it returns bool or something boolish. It's a unary predicate, it takes one argument, and then it's indirectly callable. That is, we can dereference the iterator, that's the indirection part. We can dereference this iterator type and call the predicate with the iterator's reference type. So that's what the indirect unary predicate is all about. It's just a constraint on our predicate argument. Okay, so we've got most of our drop while view. There's just kind of one little thing we need to do that we haven't really taken care of yet, which is making this a range. So we need to add begin and end operations to actually get this thing to return iterators, to actually turn it into a range, to do something useful. So we can have a bit of a think about what our begin and end operations should return. Well, what we want to do is we want to go and we want to adjust this adapter. We want to adjust the back of the underlying range to act as if we are removing some elements from the back of the range. The front of the range, however, we're leaving unchanged. That's the job of drop while view. That's the thing that drops from the front. So in fact, our begin operation, all we're going to do is just forward our underlying views begin operation. For end, however, we have to think a little bit more. We have to consider, we have to think about what we're doing a little bit more. How do we find the new end iterator? So what we want to do is we want to iterate backwards over our underlying range and discard elements whilst our predicate is true, right? Iterate from the back, discarding elements while the predicate is true. And we can twist this sentence around a bit, and to say the same thing in different words, we want to iterate the underlying range in reverse and find the first element for which the predicate is not true. Iterate in reverse and find if not. So this is how we're going to do it. in our end iterator, we are going to call the FindIfNot algorithm, and we're going to pass it reverse iterators for our base. We've asserted that this is a bidirectional range, so we know this is going to work. So we're going to call FindIfNot on our underlying range. We're going to use that predicate, and it's going to return us an iterator or a reverse iterator to the position, the first element that does not satisfy the predicate. And then we're going to call .base on this returned FindIfNot. We're going to call .base on this returned reverse iterator so that we get the original iterator, underlying iterator back out. So this is one way we could write it. Actually, I'm using the standard ranges FindIfNot, but really at the moment it's no different to the original standard FindIfNot. Another way we could write it is like this. We could take a temporary views object. Sorry, we could wrap base in a reverse view, and then we could pass that reverse view into FindIfNot and return. And again, that's going to return an iterator, and we can call .base on that returned iterator. So either of these, the first or the second way, is fine. What we can't do is call FindIfNot and pass standard views reverse base directly as the first argument. That's something we cannot do. And if you're wondering why we can't do that, why I would need to do it in 2 steps, then watch last year's video because I cover that. Okay, so this now, if you were to copy and paste this into your browser, into Godbolt or something, into your editor, if you were going to try and use this, you would find this works, right? This is 20 lines of code now, and this is a working range adapter that's going to drop things from the end of our range, a bidirectional range, like a string or something. This is pretty nice. However, there's one more thing we've got to do, and that is because we were talking about the semantic requirements of a view. The range concept also has some semantic requirements. And one of those semantic requirements is around begin and end. And they specify that begin and end must be amortized constant time. That is basically, if we call them enough, it's a constant time operation. So that's fine for begin, because we assume our base operation, our base range meets these criteria, does this. So begin is fine, but here end is not a constant time operation, because every time we call end, we have to iterate through an arbitrary number of elements until we find the actual end. Okay, so this is a problem for a number of range. Well, a problem. This is something that occurs for a number of range adapters. So we're writing drop last while view. It's probably similar to the standard built in to the standard provided drop while view. That has this problem. Filter has the same thing. We want our begin and end to be, as I say, on average, constant time. So the way that this gets solved in the standard library, what we do is we do this find operation once, and then we cache the result. Okay, so the way we're going to do it here, there are a couple of ways you could do it. The way I've chosen to do it is we're going to have an optional variable which holds an iterator into base, and we're going to call that cached end. And in our end function, the first time we enter it, cached end is going to be default constructed. It's going to be a disengaged optional. So the first time we enter the end function, we're going to do this find if not business and find the end of the range that we're interested in. And after that, on each subsequent call to end, we're just going to return our cached value. And as I say, there are a couple of different ways that you could do this. This is the way I've chosen to do it here. And this is kind of similar to the way that that the standard library does it as well. So this is, believe it or not, this is our complete drop last while view. Well, almost. There's one more thing we have to do. And it's not really to do with drop last while view itself. That is, we want to write a wrapper factory function. So all of the standard library views, transform view, filter view, drop view, all of these, those are the view classes, but we actually have these function objects in the views namespace that are used basically as factories, factory functions to create these views. And really the best way to think about it is that these classes, transform view, filter view, etc., these are kind of implementation details. And really you should be interfacing with things via the function objects in the views namespace, right? That's the best way of thinking about it. So we're going to follow the pattern from range v3 and from the standard library. We're going to add a function object in our views namespace. Now, there is absolutely no way that I know of to make this not look hideous. All right, I'm very sorry. I've tried several times to rewrite this in a way that doesn't look awful, but it actually does look pretty nasty there. I've got to be honest. But, you know, if you look at what each line is doing, we've got a function object, overloaded call operator. It's a templated, the first argument is a viewable range. Again, we went over what a viewable range is in the last talk, if you're wondering what that is, but it's a range that can be turned into a view. And this returns a specialization of our drop last while view, where the first parameter is the viewified version of R, if you like, and the second parameter is the predicate. And then within the body of this function, we're just constructing that drop last while view and returning it. You have to say it 3 times, as Iterator likes to tell us. So yeah, there's no way of doing this in a way that doesn't look hideous. So it's just stuff we have to put up with. So assuming we've done all this, assuming we've got there, can we at last go ahead and just use our new views drop last while instead of trim back? No. No, we can't. This makes me very sad. Well, actually, of course we can. We can use our drop last while view. But the way we have to do it is by calling it as if it was a function, by calling our views function object as a function, right? What we can't do is what is here and try and use the pipe syntax, right? In C++20, third-party range adapters like the one we've just written cannot easily opt into using the pipe syntax. I said easily because if you are determined and masochistic enough, you can. Here's a kind of way you might try and do it. So this is a way that might sometimes work for GCC 11, for example. You can see we're having to use some standard library internals there, the __ adapter _ range adapter type, right? So at the moment, each and every standard library implementation does this piping in a different way. So it actually changed in GCC between GCC 10 and 11. And MSVC does it in a different way. Clang, libc++, again, I'm sure we'll do it in a different way again. Right, so yes, it is possible to look up the internals and you'd have to have a lot of if-defs for every compiler you want to support. And not just that, for every compiler version. If you are determined enough, you can get your own custom adapters working. I would very much not recommend not doing this, right? Because you're just asking for pay. So in C++20, third-party range adapters, sadly, we can't opt into the pipe syntax yet. This was identified by LEWG as an important gap that we want to fix in C++23. So Barry Resin, who has an awful lot of the standard library, an awful lot of proposal papers, and amongst his many excellent proposals is P2387, which proposes a way that third-party code, user code, can opt into this nice, lovely pipe syntax. So okay, that was supposed to be an image there that was going to be a link to Godbolt, where I was going to show you that the drop last while view did actually lead to nicer code than the reverse, trim, reverse. So this doesn't seem to have, I'm not quite sure what's happened to that image. So apologies for that. I will make sure this is fixed before all the slides go up. But sorry about that. Okay, so I can see a couple of questions. When you call FindIfNot, how does it work with the laziness of ranges? So I think I covered this. So this is only what happens when you call begin, and in fact, with the cache value, this is only what happens when we call begin the first time. So yeah, I think I probably covered this, and there's a little bit of discussion there as well. How do piped views get compiled? Is there a notable runtime performance overhead to consider? There is no runtime overhead of using the pipe syntax versus the function call syntax. It's purely a compile time thing. There might be a little bit of compile time overhead, a bit of extra operator overloading and stuff. But in terms of runtime, no, there is no runtime overhead to using the pipe syntax. There might be a little bit of runtime overhead from using lazy evaluation rather than a direct eager for loop. Whether that's noticeable or not, it depends. It depends. It always depends. It's a performance question. It depends. So another one from Dennis. Drop last while view. If we construct from vector. Yeah, if we try and construct it from a vector, this is something I went over in the last talk, but the viewable range constraint means that we could only compile it from an L value vector, and the views all would convert that. We would actually wrap it in a type called a ref view, so it would make sure that we abided by these algorithmic complexity constraints. Okay, so I can see there are a couple more questions. I am rapidly running out of time, so I'm going to move on to the next one. I will do my best to answer the questions. Perhaps we can hang on for a couple of minutes after the recording is finished. I'll do my best to get to your questions, but time, unfortunately, is marching on. I did warn you that there was a lot we wanted to get through, because I really want to get through our last problem, this mysteriously named dual shifting. So, what on earth is this all about? So here's what I'm on about. If we're given a pair of arrays and an integer value k, we want to perform a cyclic left shift of k positions across both arrays, modifying these arrays in place. So a bit of a contrived problem, but it's one that I actually think is quite interesting, because I don't know of a way of solving this neatly, sort of naively. So, for example, given arrays v1 is 1, 2, 3, v2 is 4, 5, 6, 7, and we want a shift of 2 places, we should obtain. So after the function is run, we want v1 to contain 3. So you can see the value 3 has been shifted left 2 places, and then we've shifted the values 4 and 5 from v2 into v1. And then v2, well, the values 6 and 7 have both been shifted 2 places to the left. And the values 1 and 2 have been shifted left from v1 all the way round to the end of v2. So this is a cyclic shift. Cyclic shift, what's that? That's a rotate, of course. If we're in, I can almost hear the groans over Zoom. If we're in person, I'd expect a large groan from the audience. As I said, it's been a long week. I do apologize. I'm sorry. But hey, so how do we go about writing this a function to do this? So as I said, this is something that actually I don't kind of know how to do naively. I had a go at doing it. I ended up with an awful lot of code that was basically re-implementing standard rotate, and not very well. Because we really want to be able to use standard rotate to do this. But at the moment, the only way I know of to do this, or the only way that came to mind, I'm sure lots of other people much smarter than me immediately thought of a way to do this. But the only way I thought to do it was to copy the contents of V1 and V2 into some temporary working vector. I've helpfully named it Big Vec because it's going to be quite big. This contains all of V1 followed by all of V2. We do a rotation on this Big Vec by k places. And then finally, we copy out of our Big Vec back into V1 and V2. So we pretend that we modified them in place. So yeah, we can do it, but you've got to admit this is not very nice. This copy in, copy out, using a double the memory that we need to. It's not great. And there is probably I'm sure there is certainly a way to write this, but you're basically going to be doing manual rotations. I don't know of a way that we could use standard rotate to do this. If we were using range v3, however, we could use a view that is in range v3. It's called concat, views concat. And what concat does is it takes two ranges, or in fact in range v3, an arbitrary number of ranges, and it is an adapter which presents itself as being a concatenation of all of the underlying ranges. So this is also present in other programming languages. Most other languages call it chain. So we're going to have a go at writing a simplified version of a chain view, right? As we're going to see, there are lots of ways that you could extend this. We're just going to, in the not very long that I have left, we're going to just really do a really simple basic version of chain view. But there are lots of ways that you could go and extend this. I'm just, going to kind of get you started. Okay, so we're going to start off as we did with our last range adapter. We're going to inherit from view interface, and we're going to, this time we're wrapping two underlying ranges, V1 and V2. And again, you can immediately sense, okay, I kind of want to make this variadic, but for simplicity, we're going to start off with just two. And both of these things need to be views for exactly the same reason as they did last time. It's because we're going to have these as members and we want to meet the semantic requirements of the view concept. We're also going to add this second constraint. We're going to require that V1 and V2 have exactly the same reference type and exactly the same value type. So this is a more strict constraint than we perhaps really want, because don't forget our chain view has to return a consistent type from its iterator operator star, right? It can only return one type. It can't change as we're iterating over it. So we want to choose what type we're returning. For now, that's perhaps a bit tricky to do. So we're just going to constrain. We're going to require that our views have the same type, exactly the same range reference type, and exactly the same range value type. Just makes things easier to get started. And then we're going to start off with much the same boilerplate that we had last time. Last time we were holding a view and a predicate. This time we've got two views, default constructor and a constructor that just initializes our two member variables. And now, just as we did last time, we've got to start considering, okay, how do we iterate over these things? What do we return from begin and end? Well, last time we were in quite an easy case because all we really wanted to adjust was the end value. So we could still use the same underlying iterator types from the base range. This time we need to do something more complicated. This time we need to write a custom iterator and a custom sentiment. So luckily, we've all just seen how to write a custom iterator. There was a reason I did all that Fibonacci stuff. So fresh in your mind is how we write iterators. So we're going to have a go at writing the custom iterator for our chain view. So here we go. Here's where we start off. And we're going to start off exactly as we did for the Fibonacci iterator, a couple of pieces of boilerplate. The value type, we're going to say it's the same as the value type of V1, which is also, as we've said, the same as the value type of V2. And we're also going to choose our difference type. We haven't required that V1 and V2 have the same difference type. So we're going to say that the value type, the difference type of our iterator is whatever the common type is of the difference types of our underlying views. And this maybe gives you an idea of how we could handle underlying views which don't quite have the same value type or reference type. The other thing we're going to do, and this is not required, it's just for convenience, we're just going to add a type def reference, which is the range reference T of V1 and V2, because we've, for now, asserted the same thing. Okay, so we're going to add a couple of constructors to our iterator. Iterators are required to be default constructible, so we add one of those. And the other thing we do is we add a constructor that takes as an argument our parent class and uses that to initialize a pointer member, which just points to our parent. So this is something that view iterators very commonly do. Usually the parent view will hold some state or hold some information that we want to be able to get at. And the way we can do that is by holding a pointer pointing to our parent object. So this is not, so lifetime isn't really an issue here because iterators aren't in general required to be able to outlive their parent object. You think about like a vector iterator, it's effectively a pointer into the vector's data array. So this is kind of the same thing here. So there aren't any new lifetime issues going on. We're just going to hold a pointer to our parent just because this is going to come in handy, as we'll see shortly. The next thing we want to do is we want to add a couple of other member variables, iter1 and iter2. These are iterators into our underlying view. So iter1 is an iterator into our first view, iter2 is an iterator into our second view. So what we want to do is as we're iterating our chain view, first of all, we're going to iterate all the way through the first range. Then we're going to iterate all the way through the second range. And only once we've done that is our chain view iterator. Only then is its job done. So in order to do this, we're going to hold an iterator into the first range, an iterator into the second range. And we're also going to have this Boolean flag that's going to tell us when we're done iterating over the first range and can start iterating over the second one. Now, if you think about this deeply enough, you realize we never actually require iter1 and iter2 to be valid at the same time. So you can do this with a variant of iterator v1 and iterator v2. This can be a variant. So that's a potential optimization. There are lots of ways that you could extend this, optimize it, make it better. But we're just going to do the simple thing for now. So just as we did before, we need to add an operator star. In this case, what we're going to do is we're going to say, OK, are we done with the first range? OK, I'm going to dereference iterator 2. Otherwise, I'm going to dereference iterator 1. And yeah, I could do this with an if statement, but it's nice in one line if I use the ternary operator. So finally, just as we did with our Fibonacci iterator, we need to add two versions of the increment operator. The second one, because at the moment, starting slowly, we just want to be an input iterator. We're just going to have our our post-increment operator. I always get those wrong. Just do what our simple version did before, just return void. Our actual important pre-increment operator, it's not actually a lot of code, but it didn't quite fit on the slide, so we'll just break it out separately. This is what it looks like. It looks a bit intimidating at first, but it's not really. So first of all, we want to check, are we still iterating through the first range? If we are, OK, I'm going to increment our first iterator. And then we're going to check, have I reached the end of the first range? So this is why we needed the pointer back to our parent. And again, you might be able to think of an optimization for this. But this is the way we're going to do it for now. And if we have reached the end of the first range, we're just going to set our flag to true. And otherwise, if when we entered the function, we were already looking at the second range, we're just going to bump our second iterator. So we can put that all together. It is annoyingly, as I said, very slightly too long to fit on one slide. Alas. So I realise my time is rapidly coming to an end. So I will save you going through the sentinel, but basically we just need to wrap up the sentinel from the end of the other chain view, end of the second view, and then add a comparison operator between our chain view iterator and its sentinel. And then with all of this in place, with our custom sentinel, custom iterator, and also, again, as I said, there's no really nice way of doing this that doesn't look hideous. We have our chain view factory function, our views chain function operator, this time is a lambda. With all of this in place, we can now chain, in this case, two vectors together. Now, there are limitations to this. Of course, we're only an input range for now. Our underlying ranges have to have precisely the same reference type. So if one of these vectors was const and the other wasn't, this wouldn't work. We can only take two ranges. Our implementation is not spectacularly efficient. We can't have const iteration yet. There are lots of ways we could improve this, but hey, this works and prints 1, 2, 3, 4, 5, 6, 7. So this is pretty nice. Just in the last 30 seconds, we can, just as we did before for Fibonacci, bump this up to forward. We need to add a little bit of boilerplate. Again, the iterator category, we have to be a bit careful because we have to make sure both of our underlying ranges are both forward. But if they are, then we add a second version of the pre-increment operator that meets the requirements of the forward iterator. And we also add this equality operator for two iterators. But again, we can just default. And I suspect that should have had a constraint on it as well. Sorry about that. So with all of this in place, and as you can see, you can start to get the idea of how we might add constrained perhaps operator minus minus when we've got two bidirectional ranges, for example. So we put all of that together. We have our chain view, and we can take all of this horrible dual shift, horrible vector copies that we were doing before. And now that we've got a forward range, we can rotate works with forward ranges. So now that chain is returning forward iterators, we can use rotate with it. And we can replace all of this horrible code we had before with this one or two liner here. So this is really my favorite slide on the whole lot. We've gone through an awful lot of slides. We've really rushed through things sort of Lacoste speed today. Right. But this is really my favorite because we've used this reusable, and okay, we've only implemented as much as we needed to, but we could get some ideas of how we could expand this. We've taken this reusable adapter chain and we've used it to really simplify our code and to make things more, actually probably more efficient. And certainly if you went all in with chain and if you took it right up to random access, this is going to be much, much more efficient than doing the copy in and copy out. And it's certainly a hell of a lot less code than if you had to manually implement what standard rotate does. So this is, I think, the absolute strength of ranges. This is taking a really complicated chunk of code and turning it into something simple. This is what I love about ranges. This is what makes me excited to work on ranges, to use ranges. This is why I have given 3 talks on ranges now. But that is it. That's the end of the saga. So apologies for running a little bit over, but that's it from me. I will just have a quick look through the questions because I can see we've had a number of questions coming in, but thank you very much. Sorry we had to rush a little bit there at the end, but such is life. Okay, so what happens? I'll just answer a couple of questions and then we'll wrap up. So what happens if after creating adapter, someone changes the underlying containers values so the cache is inconsistent? Yeah, this is indeed a problem. So it's pretty much the same as iterator invalidation. So if you, it's exactly the same problem. So if you have a view that points that wraps a vector and you change the underlying vector, add elements to it, so you change, changing the underlying storage, it's going to be exactly the same problem. Do I know of any code base heavily using ranges so we can tell how it fits into production code? I don't know of any public code bases, no. I'm afraid. There is a comment there that ThinkCell, but they have their own ranges library. I don't know of any large public code bases. I've heard of some companies using this quite extensively internally, but I don't know of any that we can go and I could go and point you to GitHub on. And so, can you have a different value type while having the same reference type? Yeah, I'm not sure actually. Possibly. I'd have to think quite carefully about it, but I suspect it might be possible. I was just being extra safe. Okay, so thank you again, everybody. Thank you for the questions. Again, thank you. Again, apologies for having to go rush a little bit at the end and taking a bit more time. But it's been great. It's been an exhausting 3 years or 2 years, 3 talks. But thank you very much, and I hope to see you again at some point in the future. Thank you, everybody.